Hi guys, here we're going to talk about different chemical reactions. So you'll need your notes, which is your pen and paper. So to quickly review, we've actually gone through nuclear reactions, which are completely different than chemical reactions. Nuclear reactions are transmutations. So one transmutation is a natural transmutation. Here we have 22792 uranium produces 22390Th plus 42He. That He particle is an alpha particle. So if you notice, these are actually going to have uranium on one side, Th on the other, and He on the other. So between the left and the right-hand sides of the reactions and the products, you completely change the type of element that we have, or the element that we have itself. So this is a natural transmutation. We also have artificial transmutations. So to recall, the difference between natural and artificial transmutations is that artificial has been bombarded by a particle. So in this case, we have beryllium being bombarded by a positron. It produces a lithium and a helium. Natural transmutations have one reactant, artificial have two. That'll help you out with some Regents questions. We also have fission. Fission occurs in our nuclear power plants. Here we have 23592 uranium being bombarded by a neutron, and then that uranium breaks down to smaller particles. We also have fusion, which occurs in the sun and stars. We have hydrogens being combined to form helium. So with all of these nuclear reactions, we start out with one element and produce a completely different element. In chemical reactions, the elements themselves are the same, but they're just rearranged, or they have different partners. We've already looked at organic reactions in Unit 2, so if you need help with saponification, esterification, fermentation, all of those, go back to some of those Unit 2 videos or your notes for those. What we're going to do here is some more chemical reactions in addition to all those organic ones we've talked about. We're going to talk about combination and synthesis, decomposition, single replacement, double replacement, and we're going to review combustion as well. So combination or synthesis is when we take two reactants and form them into one single product. The reactants may be elements or compounds. So for example here, we're taking zinc and iodine and producing zinc iodide. We have two reactants, one product. In combination or synthesis, we'll end up with only one product, so that'll be a good kind of word of wisdom for you as well. We also here have calcium oxide and water to produce calcium hydroxide. So if you see here, in our reactants, we have two reactants and plus sign, and we only have one product. Same thing here, two reactants and one product. It can be two or more reactants, but at the end you'll only have one product. You're only going to create one thing at the end. Decomposition is the opposite. So back in bio, we know decomposition is breaking down. Here we have one reactant, which is a compound, and that breaks down to give you more than one product. So here we have H2O2, which is actually hydrogen peroxide. So you see this in the grocery store or the pharmacy. Sometimes we use that to kind of clear out some cuts. And hydrogen peroxide is in a brown container. It's always going to be in a brown container because when it's exposed to light, it breaks down into water and oxygen, or it decomposes into water and oxygen. So here you have one reactant and two products. And to show you kind of how that happens, you're taking two hydrogen peroxides and we're breaking the bonds that are occurring between them. So we know we need to have, two HOHs. Remember from balancing chemical equations, we can write H2O as HOH, and then an oxygen-oxygen bond. So we can have an OH here, OH there. So these can combine with those. So really, what you end up with is an oxygen and two waters. So pretty much an O with that. So again, this is decomposition. You're starting out with the reactants, in this case hydrogen peroxide, and then you're producing more products at the end. Single replacement. So this is when it starts to get maybe a little tricky. An element reacts with a compound and replaces one of the elements in the compound. So metal replaces a metal, or non-metal replaces a non-metal. So in this case, you have zinc, and then HCl. This zinc is going to actually kick out the H and then combine with the Cl. So here at the end you have ZnCl, and then the H is kicked out. It's diatomic, so we actually make it H2, and we know it's in a gaseous form. We actually use table J to do this, so make sure you have table J out as well. We're going to check to see if these single replacements actually occur. So the way we have table J set up, the most active metals are at the top, the least active are at the bottom. And they're all based off of hydrogen, which we know isn't a metal, but in this case, we know that it's based off that hydrogen standard. So the metals are on the left-hand side, non-metals on the right-hand side. So we're looking at Cu, which is right here, and we're going to see if it's more or less reactive than Ag. So we see that Cu is more reactive than Ag, so that Cu can kick out the Ag, to produce 2Ag and CuNO3. So the Ag is now all by itself. It's the least reactive between copper and silver. So here we have Cl2 and 2NaI. We know that Cl is a nonmetal, so we're going to check to see if that Cl will kick out that I. So we're going to go over the nonmetal section here. We have Cl2 and I2 right there. Cl2 is more active than I2, so the Cl will actually kick out the I and then combine with sodium. Oops. Well, I don't think it's written there. That's okay, we'll write it ourselves. So we know that the Na will combine with the Cl, and then I2 is all by itself. I2 is going to be, it's a Hunkelbrief. So iodine is a Hunkelbrief, so it will form that, the diatomic molecules. And then we have NaCl over here at the end. Alright, so next is double replacement. Here, two ionic compounds exchange ions to form new compounds. So we'll take a look here. We have Na and Cl. So I know I can form them into ions, Na plus and Cl minus. And over here we have Ag plus and NO3 minus. Remember, NO3 is something from table E. It's a polyatomic ion from table E. So we'll keep all that together. And then here we're actually going to check to see what the products will be. Since Na and Ag are both going to be positive, it's more likely that the Ag is going to combine with the Cl, and the Na is going to combine with the nitrate. Now these reactions will occur if one of the two, meaning if AgCl or NaNO3 is going to be a solid. To figure that out, we have to use table F. Table F is brand new to you guys. So to read table F, we see that we have on the left-hand side ions that form soluble compounds, meaning that these will dissolve. There are certain exceptions, so these will not dissolve in water. They'll form solids. Actually, I'll write that down here too, solids. Whereas the ones that will dissolve will be aqueous. And then if the regions had more room, they probably would have made this into one one table in general, but we can actually see over here we have insoluble compounds here, meaning that they won't dissolve, and that these form solids. And that's supposed to be an S there for solid. The exceptions will dissolve, and these will be aqueous. So let's take a look here. Any of the group ions will dissolve, and there's no exception. So if you have a group 1 ion, it will dissolve in water. Ammonium will dissolve, so will nitrate, acetate, hydrogen carbonate, and chlorate. Here we have the halides, group 17. They will dissolve except when they're combined with silver, lead, or mercury. Same thing here with the sulfates. They will dissolve unless they're combined with silver, calcium, strontium, barium, or lead. Over here on the right-hand side, carbonate will not dissolve. It will be a solid unless it's combined with a group 1 ion or ammonium. Chromate will not dissolve in water unless it's combined with a group 1 ion, calcium, magnesium, or ammonium. Phosphate will not dissolve unless it's combined with a group 1 or ammonium. Sulfide will not dissolve unless it's combined with a group 1 or ammonium, so kind of the same thing there. and hydroxide will not dissolve unless it's formed with a group 1, calcium, barium, strontium, or ammonium. So a table F, this is what we use in order to figure out what will dissolve versus what won't dissolve, and what forms these double replacement reactions. So here we needed to see if sodium would combine with the nitrate and if silver would combine with the chlorine. So going back, if we wanted to form, let's see, silver chloride, well, we'll come down here to the halides. This is where chlorine is. And chlorine, excuse me, sorry guys. Chlorine will dissolve in water. It will be aqueous unless it's combined with silver. So we know that silver chloride will be a solid. So the reaction can occur. And then the other one was sodium nitrate. The other compound that could have formed, so sodium nitrate. Sodium is a group 1 ion that will dissolve in water. It will not form a solid. And nitrate is also on this list that will not form a solid. It will be aqueous. So this reaction will occur. AgCl will be a solid, and sodium nitrate would be aqueous. We'll come over here to H2SO4 and 2NaOH. Again, we'll check to see if H will combine with OH, and that will happen with our sodium sulfate as well. So here we end up with Na2SO4 and 2H2O. These will both be aqueous, so really what ends up happening is that they all end up being in kind of one solution or one mix together, whereas the first reaction here, you'll end up seeing something called a precipitate. And a precipitate is when a solid forms, when you have two aqueous solutions. So we'll kind of review combustion. We've already seen these in organic reactions, but these can be pretty common, so I just want to remind you of them. This is when we have a hydrocarbon or other organic compound that burns in oxygen, and we produce carbon dioxide, water, and heat. So here, let's see, we have butene combined with oxygen to produce carbon dioxide, water, and then heat. So this is a combustion reaction. It is a type of chemical reaction. So now we're going to quiz ourselves. We're going to check to see what type of reaction each of these are. So go ahead and make your decision. Alright, and this one ends up being a single replacement reaction. Here, the aluminum will end up kicking out the hydrogen and forming with the sulfate at the end. So we have aluminum sulfate, and then hydrogen's all by itself, meaning not combined with another element. So this is a single replacement reaction. Quiz yourself with this one. And this one's a combination or a synthesis. We started out with, in this case, 2 reactants and just produced one big product at the end. This one ends up being a decomposition. We have potassium chlorate decomposing into potassium chloride and oxygen. So this one is your combustion reaction. You have an organic compound plus oxygen producing CO2 and H2O at the end. This one is a double replacement reaction. We have acetate here combining with lithium, and then the waters themselves, hydroxide combines with hydrogen to produce water. Right, so we kind of have 2 partners, each of which are switching. So to summarize, make sure you memorize what to look for in each of the types of reactions. So for example, in a decomposition, you're looking for one reactant and several products. In a combination, you're looking for several reactants and one product. In combustion, you're looking for an organic molecule combined with oxygen and producing CO2 and water. For single replacements, use Table J, and for double replacements, use Table F. We'll be practicing these in class together, guys. Take care and have a good day.